Hello everyone. In this lecture, we'll be seeing the third property of function, that is necessary and sufficient condition for a function to be invertible. So a function f from a to b is said to be invertible if and only f is both on1 and on2. On1 and on2 in the sense we are telling f is a bijective function. And also note that in this statement, if and only if condition has been given. If and only if condition means both the directions we are going to prove. First, we are going to assume f is invertible. We are going to show that f is both on1 and on2. In next direction, we are going to assume f is both on1 and on2. We are going to show that f is invertible. So the first part, we are going to assume f is an invertible function. F is an invertible function means inverse exists. So I am going to name that inverse as F inverse. So F inverse will be a function from B to A. F inverse is a function from B to A and F is a function from A to B. And observe that if I take F inverse composition F, I will get I A. If I take F inverse composition with F on right side, I'll get the map identity B. IA represents identity map on the set A and IB represents identity map on the set B. So note that we can recall this by where we are multiplying this one. So if we take composition of F inverse with F at first, then we'll put the domain of F. So if we take composition of F inverse with F in the second place, we'll put the identity map on codomain of F. So this is what we are going to prove. To prove F is on1 and on2, since F is invertible, there exists a function F inverse from B to A such that F inverse composition F will be IA and F composition F inverse will be IB. These maps IA is nothing but identity map on A and IB is identity map on B. So now we are going to show that F is 1, 1. So let us recall 1, 1 condition. Given that F is a map from A to B. So to prove 1, 1, we are going to assume F of x1 equal to F of x2. And we have to show that x1 should be equal to x2 for any x1 comma x2 belongs to A. The same assumption we have taken here. Let x1, x2 belongs to A with the condition that f of x1 equal to f of x2. Now since I am having f inverse in hand, we are going to apply f inverse to both the sides. So we are going to take f inverse of f of x1 equal to f inverse of f of x2. So now here we can apply the composition definition. So it is F inverse composition F of x1 will be equal to F inverse composition F of x2. Observe that F inverse has been multiplied in first place. So we are going to put the domain identity map. So it is IA of x1 equal to this is IA of x2. Identity map is nothing but every element will be mapped to itself. So x1 will be mapped to x1 and x2 will be mapped to x2. So see that we have showed x1 is equal to x2. Therefore, f is 1, 1 function. So next one, we have to show f is onto. So to prove f is onto, we have to choose one element from the codomain B. So we are going to choose one element from the codomain. Let y belongs to B. For this one, I am going to find one pre-image in A. Also note that we are having F inverse in our hand. F inverse is a map from B to A. Since this element Y belongs to B, we can find the image of Y under the map F inverse. So, we can find F inverse of Y, which will be in the codomain of F inverse, that is nothing but A. So, I am going to name this element F inverse of Y as X. Clearly, we can observe that X will be an element in A. Now, I am going to show that this X is the required pre-image of Y under the map F. So, we are going to find F of X. I need to show that F of X is Y. So, we can take F of X is equal to F of, already know that X is nothing but F inverse of Y. So, we can put F inverse of Y. Here we can apply the definition of composition. So, it is F composition F inverse of Y. F composition F inverse. Observe that F inverse has been multiplied in second place. So, we have to put the identity map on codomain of F. Codomain of F is nothing but B. So, it will be I B of Y. Identity map is nothing but every element will be mapped to itself. So, Y will be mapped to Y. Observe that we have started with the F of X and we have shown that Y. So, if we choose one element Y in B, I am able to find one element X in A such that this X is the pre-image of Y in A under F. So every element, since we have taken any arbitrary element, for every Y belongs to A, we can find one pre-image X in A. Therefore, F is a surjective map. Surjective in the sense it can be also called as onto map. So in this theorem, we had shown that whenever F is invertible, F will be 1, 1 and onto. So we have finished one part and the another part is remaining. Another part we are going to assume F is 1, 1 and onto and we have to prove F is invertible. So first for this one, we are going to define a function g from B to A because see that F from A to B is an onto map. Since it is an onto map, so I can define map from B to A. G map as follows. So observe that for every Y in B, since F is onto. So for example, let us consider this as A and this as B. This will be our map F. Okay. Since F is onto, if I have any element in B, correspondingly I will have a pre-image in A. So name that as, so if I take Y here, I'll have one pre-image in A. I am going to take that pre-image F of X is equal to Y. I am going to give that element as G. So this can be written as G of Y is equal to X. I am going to give that pre-image as the image of Y under the map G. And also note that it is not possible to define two elements under the map G because if we find the pre-image of Y under F, only one pre-image will be there because the function is 1, 1. We cannot have two pre-images. If we have two pre-images, the 1, 1 condition will be neglected. So, it is not possible to have two pre-images. I'll have only one pre-image. So, I'm going to give that pre-image as the image of Y under the map G. That's what we have written here. Since F is 1, 1, this pre-image X will be an unique element. So, we are going to define that X as G of Y. Then, for all X belongs to A, observe that G of, we are going to find the composition F of x. This will be equal to g of f of x. And observe that f of x is nothing but y. So this can be written as g of y, and the value of g of y is nothing but x. This will be equal to x. So observe that G composition F maps every element to itself in A. So G composition F will be IA. Similarly, if we take F composition G of Y, this can be written as F of G of Y, and we know that g of y is x, so we can write it as f of x, and f of x value is y. So observe that f composition G map, it maps every element in B to itself. So f composition G will be identity element on B. So one more thing, we are talking about inverse of f. So let us observe the characteristics of G. If I multiply or take composition of G in the first place with F, I am getting the identity map on domain of F. If I take composition of G in the second place of F, I am getting the identity map on codomain of F. So this property is nothing but the property of F inverse. So we can conclude G is the required F inverse map. So F will be an invertible function. So the reverse part also we have shown, that is assuming F is 1, 1 and on 2, we have shown that F is invertible. Thus the necessary and sufficient condition for a function to be invertible is the function should be a bijective function. Both the condition 1, 1 and on 2 is necessary to prove this path.